Homework 8, Inverse Functions, Video 5. In the last video, we determined a visual way to determine if a function is invertible or not, if its graph passes the horizontal line test. In summary, if you can hit a graph more than once with a horizontal line, then that graph is not invertible, the function is not invertible. But if you can only hit it once with the horizontal line, no matter where you hit it, then the function is invertible. But there is a strong relationship between the graph of a function and its inverse. For example, let's take g of x equals the square root of x. We know what its graph looks like. But what the heck is its inverse function? Because it can't be that. We've already decided that x squared is not invertible, so it can't be the inverse of something. So what will it be? Well, let's think about it. By actually keeping track of some points. Let me draw this graph a little bit more specifically, because I do want to draw a picture that is pretty accurate. And everything I'm going to draw is going to live in quadrant 1, so give me 1 second to get this set up nice and neat. So we'll go mark, 7, 8, 9, 10, 11, 12, 13, 14, 16, we'll put one more 17 there. And then let's go across here and go same increments, inches, 2, 3, 4. Come on, marker, you're better than me. I just don't need you. 1, 2, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Okay. So I just marked this all the way from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's going up 16 in each direction, and they are measured in inches so that it's consistent. Let's just graph this one real quick by plotting some points. I know what the shape is, but let's get some specific points. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 3, excuse me, the square root of 9 is 3. Let me find 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So right about here. And then the square root of 4 is 16, so that would be right about here. So that's the worst looking half parabola I've ever drawn, but let's just pretend that it's pretty accurate. All right, so the points that I used are 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. The square root of the x's is equal to the y. Well, whatever the inverse function is, it's supposed to reverse this, meaning that, let's take it in reverse. If this function turns a 16 into a 4, then this function over here should turn a 4 into a 16. If this function turns a 9 into a 3, then its inverse should turn a 3 into a 9. If this function turns a 4 into a 2, then this function turns a 2 into a 4. 1 and 1 and 0, 0 are easy. So in order to get this function's graph, I would just have to switch the coordinates. 0, 0, 1, 1, 2, 4, 3, 9, and then 4, 16 is going to be way up here. So it's kind of the same shape, it's just going in a different direction. It's really kind of hard to see what's going in right here in this spot. So I'm going to zoom in on it over here just to show you what's actually happening. 1, 1. The top graph is looking like this, and the bottom graph is looking like that. So if you zoom in on that little part where they overlap, it looks like that. So what's going on here with the graphs, and what the heck is this function? Because it kind of looks like a parabola, but not all of it. Well, it is a parabola. Because let's be honest, aren't I just squaring all these? But you just said that squaring wasn't invertible. I literally opened that marker at the beginning of this video. By the way, I made it when I threw it in the trash can. Ooh, that's good. G of x equals x squared. But we just got finished showing earlier that this was an invertible, but think about it for a second. This function is not this graph, and why not? Because that function's graph is the whole parabola, and this one is just the right half of it. So yes, squaring and square rooting are inverses if you make it what's called a domain restriction. We have to restrict the parabola to only the right half of it. And on the right half of it, the x's are positive. So the way you implement a domain restriction after a function is you just say something like x is greater than or equal to 0. So I kind of lied earlier when I said squaring and square rooting are inverses. They are, but you have to restrict your squaring function to only squaring positive numbers, which fixes the problem we had earlier. The problem we had earlier is that we were squaring numbers like 3 and negative 3 and getting the same answer and couldn't get back both 3 and negative 3 out of this function. But if we restrict our domain to the squaring function to just non-negative numbers, it fixes that problem. Plus, it kind of shows a relationship between the graph of the two functions. You can see a little more clearly in the zoomed-in version. These guys are mirror images of each other, but they're not mirror images across the x-axis. They're not mirror images across the y-axis. They're mirror images across this diagonal line. So the relationship between the graphs of a function and its inverse, the graphs of f of x and f of inverse of x are mirror images across the diagonal line y equals x. So in your homework, when you're given one function's graph and asked what does its inverse graph look like, all you have to do is flip it across that diagonal line. But the easiest way to do it, especially if you've had ordered pairs, is to reverse the pair. Of course, if your x and y are the same, reversing the pair doesn't change anything. But that's how you can visually build the graph of a function's inverse, by taking the points off of the graph of the function, reversing the ordered pairs, and replotting them. My session has ended. Oh, that wasn't very nice, but we'll go back into the homework. All right, so that's the relationship between a function's graph and its inverse's graph. Mirror images across the diagonal line y equals x.